Today we are continuing our discussion of differentiability. Today we're going to try to chug through and prove some of our familiar identities from Calculus 1. We're going to talk about product rule and chain rule, quotient rule, and we're actually going to be able to prove these now. So let's start with this following fact. If I have a function that's differentiable at p, then it's also continuous at p. So differentiability implies continuity, and in fact it implies more than that. But if a function is differentiable at p, then it has to be continuous at p. So let's go through the proof. So let's note that f is continuous at p if and only if the limit as x goes to p of f of x equals f of p. And this happens if and only if, let me subtract f of p from both sides, and that's a constant, so I can pull it inside the limit. So this is a characterization of continuity at p. So f is continuous at p if and only if the limit as x goes to p of f of x minus f of p is 0. So I'm going to use this characterization to prove that if a function is differentiable at p, then it must satisfy this condition, which means it's continuous at p. So I'm going to say assume f is differentiable at p. So if you remember the previous lecture, differentiable at p means a certain limit exists. So I'm going to write down limit as x goes to p, f of x minus f of p. I would like to show that this is 0. So right now I don't even know that the limit exists, but I'm going to use some limit laws, and I'm going to get a limit that exists, and that's going to let me know that everything in between exists. So I'm going to multiply and divide by x minus p. Now I'm going to split this into two limits. And we can do that because of our limit laws. Okay. So the limit of a product is the product of the limits. On the left, the limit as x goes to p of f of x minus f of p over x minus p. That is f prime of p by definition. Okay. So this limit exists and is equal to f prime of p. So we've assumed that f is differentiable at p. And that means, by definition, that this limit in the first parentheses here exists. That's what it means for f to be differentiable at p. And f prime of p, this is the definition of f prime of p. So this is equal to f prime of p because that's the definition of f prime of p. Now the limit as x goes to p of x minus p is 0 because the identity function, say g of x equals x, is continuous. Okay, so this limit is 0. So we get f prime of p times 0, which is just 0. Okay. So the limit as x goes to p of f of x minus f of p is 0, and using this characterization of continuity, we deduce that this function, which is differentiable at p, must also be continuous at p. So now we're ready for the product rule. Okay. So if f and g are differentiable at p, then so is f times g. And we have this formula for the derivative. F times g derivative equals f prime times g plus f times g prime. Now, this rule says if f and g are differentiable at p, right? So it says at p. Okay? So we say a function is differentiable if it's differentiable at every point in its domain. And so if f and g are differentiable at every point in their domains, then so is the product. Okay? So we might leave the at p off and just say if f and g are differentiable and so is the product, and f times g prime equals f prime g plus f g prime without all the p's in here. But it's true even if we only assume differentiability at a single point. So let's prove it. So what I would like to do, okay, so this is how we show something is differentiable. This is one of the ways that we show something is differentiable, is we have to look at the definition. Okay. So the function in question that we're trying to show is differentiable is the function f times g. So I do the limit as x goes to p of that function, f times g, evaluated at x, minus that function, f times g, evaluated at p, over x minus p. if I want to show that f times g is differentiable, I want to show that this limit exists. Okay? So this is equal to the limit, just by definition, of the function f times g. That's f of x, g of x, f of p, g of p, over x minus p. Now I'm going to do a pretty common trick here. I'm going to do it this way. So what I've done is I've subtracted and added f of x times g of p. And since I subtracted and added it, these two things are equal. I didn't change anything by adding and subtracting the same quantity. So here, well, I'm going to use my limit laws. I'm going to split this fraction up into two fractions. In the first fraction, I'm going to factor out an f of x. I had it right the first time. I'm going to go back. So I'm going to put p, x, p, x. It doesn't matter which way we do it, but I want it to end up looking like the formula that we have up here. So I'm going to have f of x minus f of p over x minus p times g of x plus limit as x goes to p f of p, nope, parentheses, g of x minus g of p over x minus p. Okay. So what I've done is I've taken this fraction, I've split it up right here in the middle to two terms. On the first terms, I factor out the f of, or the g of x. On the second one, I factored out the f of p. Now I'm going to use my limit laws. Limit x goes to p, f of x minus f of p over x minus p, limit x goes to p, g of x. The first one plus f of p, so p is constant. F is not constant, p is constant. So I'm just going to pull that f of p to the outside of the limit. Limit x goes to p, g of x minus g of p over x minus p. Okay. So now, this first limit, limit as x goes to p, f of x minus f of p over x minus p, that is f prime of p by definition. That's the definition of f prime of p. Okay. So, because we've assumed g is differentiable at p, and by the previous fact, we know that g must be continuous at p. So if g is continuous at p, then the limit as x goes to p of g of x is g of p. So this f of p is just f of p, and then this limit over here is the definition of g prime of p. And we did it. Okay, so we proved it. We proved the product rule, and that's it. Okay, so I'm going to take a slight diversion and give an explanation for why the product rule works. So, what I'm going to say the definition of a derivative means if I take my function at f of x and change the input very slightly, the derivative is basically the ratio of change in function to change in x, which means if I change x by a tiny amount, dx, then the output is going to change by about the derivative times dx. Okay? So this f prime is a rate. It's the rate of change between f and x. Right? So if I change x by an amount dx, the f is going to change by about dx times the rate f prime. So I'm going to draw a picture. Okay. So here, this is going to be f of x. is going to be g of x. And then this big part is going to be f of x plus dx. So I change x by a tiny amount, dx, and then the output changes from the smaller line segment to the larger line segment. So this length represents the original value of f of x, and I change the input by a little bit, and that changes the output by a little bit, by this small change. Right? So that small change is this part, f prime dx. Okay, so here's f of x. I change the input by a little, and the output changes by a little. This f prime dx is approximately the change. Okay? So over here, this whole part is going to be gx plus dx, and the part over here, g prime dx. So now the product, I'm going to have f of x plus dx times g of x plus dx. Well, I'm going to multiply the whole square. So I have this length by that length. That's the area of the entire square. I'm going to subtract f of x, g of x, which is the area of this interior square. Okay. And this is telling me how much the product changed. So I started with the product, which was originally the area of that shaded square. That's the original product. And I change x by a small amount, dx. And now f changes a little bit, g changes a little bit, and then the new product is the area of the bigger square. Okay. So this is about f prime dx times g plus, say, g prime dx times f plus f prime dx times g prime dx. Right? So this f prime dx times g is the area of this top rectangle up here. The height of this top rectangle is f prime dx, and the width of it is g of x. So I have this rectangle here has that area. This rectangle over here on the right has that area because the width is g prime dx and the height is f of x. So I should have g of x and f of x here, but I don't really care. And then this part up here is has height f prime dx and width g prime dx. So I have the area of this piece is f prime dx times g prime. And so the area of the big square, rectangle, so I drew it as a square, but it probably is going to be a rectangle. The area of the big rectangle is this. The shaded rectangle is this. I subtract, and I just have the areas of these three pieces, which is what's over here. Now I want to divide that by dx. And take the limit as dx goes to 0. Okay? So over here, this part cancels. And when I take the limit as dx goes to 0, this part just stays f prime g, because there's no dx that's changing. Over here, this cancels, and I get g prime f. Over here, this dx will cancel with that one, but this one's still going to 0, so this entire term goes to 0. And there's my derivative. So I have this piece that matters, this piece that matters, and this piece that doesn't. And so the f prime dx times g and the f g prime dx, those are the part that matters. Those are the parts that matter, and those are the terms that show up in the product rule. So now I'm going to do some important derivatives. Okay, so we know power rule. Derivative of x to the n is nx to the n minus 1, where x is a variable and n is a constant. So right now I'm going to prove it for n equals 0, 1, 2, etc. Okay. So x to the 0 is constant. Okay. So let's say f of x equals x to the 0, which is constant. F of x minus f of p over x minus p is 0 for all x, for all p, because the numerator is 1 minus 1. Okay. So I take the limit as x goes to p. Well, it's a limit of a bunch of zeros, so it's 0. Okay. And that gives me the n equals 0 case. Okay. Derivative of x to the 0 is 0x to the negative 1. The 0 times whatever is just 0. Okay. So we prove the n equals 0 case. So let's do the n equals 1. We do x minus p over x minus p. Limit as x goes to p. Well, this is the limit of 1. Limit of a bunch of 1s is just 1, so we did it. Okay. So derivative of x to the 1 is 1x to the 0, which is just 1. So we prove those base cases. Now I'm going to work by induction. So I'm going to do x to the n plus 1 equals x to the n times x. If I do the derivative, then by product rule, I'm going to have x to the n derivative of x plus x to the n x derivative. Okay. So I'm working by induction. I'm assuming that I know the derivative of x to the n and the derivative of x, and I'm trying to compute the derivative of x to the n plus 1. So here, by the inductive hypothesis, derivative of x to the n is n x to the n minus 1, and that's still times x plus x to the n times 1. Okay. So this is n x to the n minus 1 times x, so I get n x to the n plus x to the n. This is n plus 1 x to the n, and wouldn't you know it, that's what it's supposed to be. Right. So we proved this for n equals 0, 1, 2, 3, etc. So we got it by induction. Here we use the product rule. Okay. So part B was, if I want to do 1 over x prime, this is negative 1 over x squared, as long as x is not 0. Function is not defined at 0, so it can't be continuous at 0, so it can't be differentiable at 0. Everywhere else is differentiable, and this is the derivative. So let's prove this. So I want to do 1 over x minus 1 over p over x minus p. I want to take the limit of this as x goes to p, and I want to show this is negative 1 over p squared. So this is equal to, let me first rewrite it like this. Get a common denominator over here, p minus x over px times 1 over x minus p. This is 1 over px times negative x minus p over x minus p. These cancel, I get negative 1 over px. Now I take the limit as x goes to p, 1 over px, I get 1 over p times p. Well, sorry, with a minus, forget the minus, negative 1 over p squared. We did it, right? So this thing, I decided I don't want that. I'm going to throw it away. So let's do chain rule, which I presumably have written down here somewhere. Okay. So if g is differentiable at q, and f is differentiable at g of q, which I'm calling p, then the composition f of g is differentiable at q, and the derivative is given by our usual chain rule formula. So I'm going to cheat a little bit. I'm not going to do the full proof. So I'm going to say the idea is, it's quite technical, you have to worry about if g prime of q is 0 or not. Okay? But the idea is, let me just write it down this way, limit as x goes to q of f of g of x minus f of g of q over x minus q. Okay. If I want to show that this composition f of g is differentiable at q, then this is the limit I need to look at. Okay. So what I'm going to do is have limit as x goes to q of f of g of x minus f of g of q over g of x minus g of q times g of x minus g of q over x minus q. Here I'm cheating a little bit. I expect you to be able to tell me why this doesn't actually work, but this is the best way to convey the idea. Okay. And this is limit, well, I'm going to split it up into two limits using my limit laws. So over here, I'm going to say, let y be g of x. Okay. So, as x approaches q, y is going to approach g of q, which is p. Okay. So, as x gets closer and closer to q, g of x is going to get closer and closer to g of q, which is what we called p up here. So instead of having g of x, I'm going to have y. And instead of having g of q, I'm going to write p. And here, I want the limit as x goes to q, but as x goes to q, y is going to go to p. So this over here is the same effect as taking the limit as y goes to p. And now this is f prime of p by definition. This is g prime of q by definition. And now p is g of q. So we did it. So this is just a multiplication of rates. Okay, so we all know how to multiply rates. So if I tell you that my car gets 5 miles per gallon of gas, which is not great, and I know the gas costs $2 per gallon, then I could say how much money is it going to cost me to drive 10 miles. Right? So I figure out using the rate 5 miles per gallon how many gallons it takes to go 10 miles. And then I use the other rate to figure out how much money that amount of gas costs, and I multiply the rates. Right? So this is all that's happening here. So one last thing, I have it written here somewhere. Quotient rule. Okay? So if f and g are differentiable at p, and if g is not 0 at p, then the quotient, f over g, is differentiable at p, and the derivative of the quotient is given by the usual quotient rule formula. Right? So, for the proof, I'm going to say let h of x be equal to 1 over x. Now, we proved on our previous page that this is a differentiable function at any non-zero value of x. Right? So, 1 over g equals, this way, the composition. Okay? So if I take g and plug it into h, h is the reciprocal function. If I take g and plug it into h, I get the reciprocal of g. Okay? So by chain rule, if I do the derivative of 1 over g, I get h prime of g of x times g prime of x. H prime is negative 1 over x squared, if I plug g of x into that. Okay. So here I'm using chain rule. I know from a previous page that if h is a reciprocal function, then h prime is negative 1 over x squared, and I want to plug g of x in there, so I get negative 1 over g of x squared, and that's multiplied by g prime of x from the chain rule. Okay. By product rule, f over g equals f times 1 over g, and the derivative of this product is f prime times 1 over g plus f 1 over g derivative. This is f prime over g, and so plus f, and then 1 over g prime, okay, the derivative of the reciprocal, we computed that up here. This is negative g prime over g squared. Okay, so all of these should be evaluated at p. I'm ignoring that. I'm skipping the at p notation because it really clutters things up. But technically, by the assumptions up here, I can only say that this is valid at p, not any other point. Who cares? Really, who cares? Okay, so let me get a common denominator. To get a common denominator, I'm going to multiply this part over here by g, and divide it by g as well, so I get f prime g, and then f times negative g prime is minus f g prime, and this is all over the common denominator. G squared, there's our quotient rule formula.